In this video, we are going to see in the case of the two masses suspended by a frictionless pulley, we are going to do the derivation for the velocity of the masses and the time it takes for the bigger object to hit the ground. So let's first see what's the scenario given. So we have a pulley and two masses, small m and capital M, assuming capital M to be bigger, are suspended by a pulley. And this is the scenario at time t equal to 0. And both the masses, they are at a height h above the ground. So this is the situation at t equal to 0. And what we are required to find out, part A, what is the velocity with which the bigger mass will strike the ground? Part B, the velocity of m just before the bigger object hits the ground, because we know that the bigger object will be moving in the downward direction and the smaller object will be moving in the upward direction. So what is the velocity of m? And then finally, part C, what is the time it takes for the bigger mass to hit the ground? So coming to the first part, regarding the velocity of the bigger object just before it hits the ground. So the initial velocity u with which the object started is 0, because as I explained, both the objects are at rest at time t equal to 0. So the initial velocity is 0. And regarding the acceleration, I have covered in my previous video, masses suspended by a frictionless pulley, wherein I have done the derivation for acceleration, and that is difference of the masses divided by the sum of the masses times g. And at time t equal to t, let's say the bigger object has it has hit the ground, and therefore in that time t, the height or the distance covered by the bigger object is h. Now, if you remember the three equations of linear motion and try to recollect the one that is applicable, where what is given to you is u and h, or distance or the height, and acceleration, and you are asked to find the velocity or the final velocity. So velocity v is the velocity with which the object strikes the ground. So that's the final velocity. So the equation is v square minus u square equal to 2as. So this is the equation that we use. And if you put u as equal to 0 and put s equal to h, so you will get v will be equal to square root of 2ah. And substituting the value of a from the expression above, we get final velocity with which it strikes the ground will be twice m minus m over m plus m times gh. And since it is a velocity, so as we know, velocity is a vector, so it will have two components, the magnitude and the direction. So as far as the magnitude is concerned, magnitude will be given by v, which is magnitude of the velocity vector v, and that is given by the expression that is mentioned here. And as far as the direction is concerned, we clearly see in the picture that the direction of the velocity will be vertically down. Now, one should be able to analyze the expression that has been derived. How does it really make sense in terms of the combination of the variables it is appearing to be made of? So let's take the special case. Let's consider in this expression for velocity, if I put the smaller mass as equal to 0. So what does it lead to? So the velocity will be equal to square root of 2m, and m is 0, so I can write it as gh. over m plus m. So again, this will become m. So these two will cancel, and therefore I will get it as square root of 2gh. And this seems to be a very familiar expression. Maybe you are able to recollect. So if we this is the velocity with which a object will fall under a free fall, or which is falling only under the influence of gravity. Say, for example, if we have a mass m, and which is initially at rest, and it is dropped from, let's say, a height h. My handwriting may not be so good. Please excuse me for that. And then uh, it hits the ground. Now, if we have to find out the velocity with which it hits the ground, we use the same equation: v square minus u square equal to 2gh, and u is 0. Therefore, v will be equal to square root of 2gh. So, which is same as what we got here. So, I hope you are able to relate now. The scenario of a pulley system, wherein if we drop this mass, that means if we drop this mass from the picture, or maybe let's say we break the string or the rope, uh, that will simulate the bigger mass to be falling purely under the influence of gravity. And therefore, that's a corner case or a special case of the pulley system. Yeah. So this is one way you should be able to analyze your derivation results. Let's now apply the similar logic for the part B, where we have to find the velocity of smaller object just before the bigger object hits the ground. So everything else remains the same, like the initial velocity of the smaller mass is 0 because it was at a position of rest. And acceleration, as I have explained, acceleration of both the objects will always be same. So it's given by m minus m over m plus m times g. And as far as the height is concerned, in time t, the bigger object has gone vertically down by a height h. It has covered a distance or height h. So the same height is also applicable. The smaller object would have moved up the same height h, and therefore height is h. So we are seeing the situation at time t equal to t. And therefore, we use the same equation, v square minus u square equal to 2as, which gives v equal to square root of 2ah. And putting the value of a, we get this as the outcome. Now, in terms of the magnitude of the velocity, the direction of the two velocities is different. So magnitude of the velocity is the same, but the direction of the two velocities is opposite. Let's focus now on part C. What is the time it takes for the bigger object to hit the ground, which is how much time it takes to cover the height h vertically down, and which is also the same actually for the mass m to go up by height h. So let's see what are the given. So the object started with the initial velocity of 0. It has to go cover a distance or go down a height of h, and what we also know is the acceleration, and what we need to find out is time. So if you recollect all the equations of linear motion with these as the inputs and the output as time, you should be able to figure out that the equation that you need is s is equal to ut plus half at square. So in this equation, if you put s as equal to h and u as 0, so this term will disappear. So you will get time t will be equal to the square root of 2h over a. And then if you put the value of a further into that, you will get the expression t is equal to square root of 2 times m plus m over m minus m times h over g. Now this expression will be the same, this time will be the same for the smaller object to go up by a height h. Now, for the sake of completeness of the video, uh, I have added two more parts. So part D is what is the distance covered by the bigger mass in time t. So let's see what is given. So initial velocity is 0 and time is given as t, and we know the acceleration is given by this expression, and what we are required to find is s equals to what. So essentially what we are saying is what is the distance by which the bigger object will travel in the downward direction at time t, in a time t. And of course, that will be same as the distance traveled in the upward direction by the smaller object. So if you think of the equation that meets the requirement here, out of the three equations of linear motion, it will be s is equal to ut plus half at square. And if you put the values straight away, so ut will become 0, and this will be half, and then put the value of acceleration over here, and t square. So that's the expression for the distance. And similarly for part E, for the distance covered by m, the smaller object will be covering the same distance but in the upward direction. So with respect to the displacement, if I say the magnitude of the displacement, which is the distance, is the same for both the objects, whereas the direction of the displacement for both the objects is different and opposite. Thanks for watching the video. Please like, share, and subscribe.